All right, so today we are working on the acid-base extraction experiment, and I'm going to give you kind of a brief intro on what the heck is the point of an acid-base extraction, how does it work, all of those types of questions. So first off, what is acid-base extraction for? Extractions in general are another method of purification. So um, things that you've done for purifying things before include distillation. Distillation separated things based on their physical properties. What physical property was that the distillation used? Yeah? Or you thought about it? Yeah, distillation separates things based on their solubility. Based on their boiling point. What does acid-base extraction separate things based upon? Their solubility. So the first kind of part of this experiment is going to be us looking at how different solids are either soluble or insoluble in different liquids and how that might impact their solubility. And then we will use those things that we learn to actually separate a three-component mixture using acid-base techniques and also extraction techniques. So something that we kind of worked a lot on as far as the pre-lab of this experiment was what happens when we take some molecule and treat it with an acid or a base. So let's think about that for a moment. So one thing we mentioned a lot about was pHs at the beginning. So what happens to a molecule, for instance, when it's at pH equals 2? Well, pH 2, is that acidic or basic? Yes, that is acidic, correct. So if that's acidic, what that means is that there is a lot of H3O plus around, because even if we say we're 1 molar HCl, HCl, if it's in a solution of water, is going to protonate water, and it's going to generate hydronium ion, H3O plus. And what we're going to have to think about a lot for this acid-base extraction experiment is how acidic and how basic different things are compared to each other. And the units that we can use for that are pKa values, or I guess the quantities that we know about are pKa values. So H3O plus, what is its pKa? Its pKa is negative 1.7. So pH 2, there's a lot of that around, and that is going to interact with other species that are in solution. Another thing that was said in the pre-lab was, what happens to a molecule when it's at pH 12? Well, pH 12, that's really basic. If this is really acidic, that must be really basic. And what that means is that there is lots of OH minus around. OH minus isn't an acid, it's a base, so we don't have a pKa there, but we will be thinking about this as a base when we are at high pH values. So we're going to talk through a few examples in a minute. So here we go. All right, so now we're going to talk about a specific example of thiophenol at a pH of 12. So first of all, anytime we have a molecule that's mentioned, we really need to figure out what the structure of that molecule is. That's very easy to do these days with just Google. Thiophenol looks like this. So this is thiophenol, and it says at pH 12. So what's going to happen to thiophenol at a pH of 12? So thiophenol, that's the first part that we need to think about, and then pH 12, what does that mean? pH 12 means that there is lots of OH minus around. So essentially, we have this thiophenol, and we have a lot of OH minus around. So what is OH minus? Is it an acid? Is it a base? It's a base. It's a strong base. So if we have this OH minus around, it's going to pull off the most acidic proton from thiophenol, and that ends up being this H right here. If it did that, it would get us to the conjugate base of thiophenol plus H2O. So how do we know if this is going to be a favorable reaction or not? To really know that, we would have to look at some quantitative values. We have to look at pKa's. So pKa's are of acids. The conjugate acid on this side is H2O. That's one of the pKa's that we should know. The pKa of water is 15.7 or 16. I often just write 16. And then the one over here you wouldn't necessarily know, but just like you can Google what the heck is thiophonol, you can also Google what's the pKa of thiophonol. And this is a very easy thing to do. The pKa of thiophonol is 6. What is it? I had to Google it. I don't have all pKa's memorized. 6.62. So acid-base equilibria. What happens? Well, the stronger acid is the more reactive species, and the equilibrium is going to go away from that stronger acid. So if we have a pH of 12, there's lots of this around to deprotonate that, and this is the stronger acid, so the equilibrium is going to be on this side. So if we treat this with a strong base, it's going to push it over there. What about thiophonol at a pH of 2? So this is a good time to pause the video. Think about what that would mean. Try to do the exact same thing that we did up here for at a pH of 2. So you've done that, you've taken a minute, you've paused it, you've written some stuff down. Writing stuff down is so important. Use it, do it. All right, so thiophonol at pH of 2. What does pH 2 mean? pH 2 means that there is a lot of hydronium ion around. There's lots of H3O+. Here's H3O+. And as far as H3O+ goes, it is strongly acidic. So it wants to give up a proton. So essentially, the pKa here is negative 1.7, and it's going to give its proton to SH. So it would be SH2 plus over here and H2O over here. So essentially on this side, we have our acid, which turns into the conjugate base, and then our base turns into the conjugate acid. So what do we compare to say what side the equilibrium's on? We would be looking at pKa values. Well, we don't actually have a pKa value for the conjugate acid of this thiophonol. We don't really know what this pKa is. But in all the cases that you will be seeing in this acid-base experiment, we're going to have kind of values to go off of, like the one above, where we would be able to say the equilibrium is definitely over to this side because of this specific pKa value. All right, so we've talked about how we can use pKa's to kind of say, oh, the equilibrium is going to be over there, or the equilibrium is going to be over here. But I wanted to talk for a minute just about how directly pKa's and pH's are kind of related. And it's due to, you've kind of seen this a little bit before in general chemistry, that Henderson-Hasselbalch equation, when you guys were doing pH equilibrium and kind of thermodynamics of acid-base reactions. But essentially, with that Henderson-Hasselbalch equation, what you learned was that when pKa equals pH, then the acid is equal parts protonated and deprotonated. This is according to that Henderson-Hasselbalch equation. So what does that mean? Well, let's take a look at thiophonol again. So we said that the pKa is equal to 6.62. So if the pH equaled 6.62, then 1/2 of the acid would be protonated. It would be in this form. And half of that acid, so 1/2, would also be in the deprotonated form. So there would be enough base around, just enough base, so there'd be enough OH minus around to halfway deprotonate this, and there'd be 50% of the molecules that looked like the conjugate base and 50% of the molecules looking at the acid. So how does this impact protonation and all of those things? Let's see what happens to an amino acid, which is a molecule I'm going to introduce in a minute, when we change pH. That'll be in 1 second. All right, so we just talked about the Henderson-Hasselbalch equation. When pH equals pKa, we are 50% protonated, 50% deprotonated. So what does that look like with an amino acid like glycine? And again, what are amino acids? They have an amine functional group, amino, and then acid, they have a carboxylic acid functional group. So that's why they're called amino acids. What's the relevance of amino acids? Well, all proteins are made up of chains of amino acids. So this is glycine, kind of the most basic amino acid. All the other amino acids have other R groups off of them, so they have other organic materials connected to them. But each protein has a specific string of amino acids, and that endows it with specific structure, and that relates to the protein function. But how does pH impact amino acids? Well, this is what glycine looks like at pH 2. And what do we know about these functional groups? Well, this is a carboxylic acid functional group. We know that the pKa of that functional group, that's right on our list to know, is about 5. This right here, this is an amine. It's a protonated amine. It's really similar to NH4+. If we look at the formal charge of that nitrogen, it's positive, just like that one is positive. It's got 4 bonds, just like that one has 4 bonds. So the pKa of that nitrogen, of the hydrogens on that nitrogen, is going to be around 9. Okay, so what did we say about pH and pKa? Well, when pH equals pKa, there'll be 50% protonated, 50% deprotonated. So at pH 2, we are lower than either of these pKa's, so there's lots of H3O plus around. There's enough H3O plus, that strong acid, to protonate both of those functional groups. But what happens when we get to, say we're adding base, we're adding OH minus, that is making the solution less acidic, and at pH, so we're adding OH until pH equals 6. Well, we have just passed the pKa of that carboxylic acid. There was, at pH 2, lots of H3O plus, enough to protonate that carboxylic acid. But once we get to pH 6, we are past that equivalence point, and that OH minus is going to deprotonate that carboxylic acid, which will take us to the structure here. Where we have the deprotonated carboxylic acid and the protonated amine. Again, this amine still has a pKa of about 9, and that means that since we're only at pH 6, and again this is at pH 6, it is still going to be protonated. We would have to get above pH 9 to add enough OH minus around to deprotonate that amine, and that would be the next thing that would happen. So if we keep on adding OH minus until, we'll just add a bunch. We'll just dump a bunch of OH minus in. And when we do that, so adding OH minus until pH of 11, there's going to be lots of OH minus around, enough to deprotonate that NH3. And at that point, the amino acid would look like this. NH2, hydrogenated carboxylic acid. We can kind of look at it like that with pH, how pH relates to pKa. That should give you a really good brief overview of how what we're doing in this experiment when we're adding acid, we're adding base, how that impacts the various functional groups in the molecule and makes them either neutral in some cases. The carboxylic acid is neutral here, it's charged here, charged here. The amine is charged here, it's charged here, and then when we get even more basic, it becomes neutral. So the differences of charge are going to be very important in this acid-base extraction stuff, and that's how we're going to be able to isolate molecules based on this extraction technique, based on their solubility. So more on that after we do our introductory experiments. We're going to work through the tables, essentially the extraction concepts, which is the first part of the report sheet that you guys will be doing, and then we'll have another little meeting like this. So we'll talk soon. Part one of this experiment, we're looking at just how different solutes are soluble or not in different solvents, and this is sodium chloride.
Yep. Two test tubes of sodium chloride.
Thank you. There we go. It's right there. All right. So here we got sodium chloride and water. So I'm going to add some water to that. I'm going to kind of bounce it around. We'll see what happens. I'm going to add a little bit more water. Probably didn't need to, but see that it's pretty much going into solution. If I give it a little bit more time, I'm sure it will. So let's do the MTBE while this
here I've
waits.
got methyl tert-butyl ether, a common organic solvent. I'll put a couple squirts of that into the test tube with the sodium chloride. And then I will mix that a similar way.
And you can see that the sodium chloride is now fully dissolved in the water. You can't see any pieces of it left.
Yeah, we call that soluble.
This is definitely soluble.
Then with this one, you can see the white solid sodium chloride sitting at the bottom of the liquid methyl tert-butyl ether. We call that insoluble. So that's what we're looking at here, is the behavior of these solutes within the solvents. What we see is an ionic substance like sodium chloride. It appears to be soluble in water, but insoluble in an organic solvent like methyl tert-butyl ether.
There we go. All right.
Figured it out.
Sounds good. We good?
Yep.
All right, we're good. The rest of the solubility test with the different solvents and solutes. So this is kind of on page 99, your table A, and essentially we had benzoic acid, sodium benzoate as the other solids, and we were again using water or methyl tert-butyl ether, MTBE. And the results of those, all the experiments look very similar to what we already showed you, but here's the solubility data. So so that should be pretty clear.
Record that on your report sheet.
Yep.
And we'll be back with some miscibility tests.
All right,
we're back. We're looking at the second part of the experiment now. This will be table B on your report sheet. And what this looks at is miscibility of liquid. So we've got test tubes here with a little bit of water in that. And then Dr. O'Reilly is going to go ahead and add some methanol into that same test tube and give it a shake.
All right. So
this is methanol from the green squirt bottles that are around the lab.
So we added the methanol, and we're going to shake it around. And to me, it looks like we can't really see any layers here.
Yeah, let the
Just
bubbles kind of
looks
settle
like
out.
Just one layer.
Yep, one uniform solution there.
So this would be a miscible. Methanol is miscible with water, so they're soluble with each other in any proportion.
Yep, form a solution. Now I'm going to do a similar thing with methyl tert-butyl ether. I'm going to put a couple of squirts in there. And what you can see here initially is you can see the two layers in there.
You can see the interface is essentially right there.
Yep, and I'm going to give it a shake just to make sure that keep everything equal here. And we'll bring it back up.
And again, how does that compare to this one? This one you can clearly see is just one uniform layer. It's got a bunch of bubbles on it, but that's just
two
bubbles.
layers.
That one's 2 layers.
And now one of the questions that we need to address in this is the question of which layer is which. What we have here is 2 clear liquids, and we would want to know which one is the organic layer, the MTBE, and which one is the water. So an easy test we can do there is to just add more water to the test tube and see which layer grows. So if we look at this now, if I find that darn camera.
Here we go. I'll hold it right here. Here.
There you go.
And then we're going to add more water to the top.
Add more water and we'll see which one grows. And so the bottom layer definitely grew with the addition of water, and that would tell us that the bottom layer is the water and the top layer is the methyl tert-butyl ether. So we're going to complete that exercise with the other solvent combinations in the table, and then we'll report back with the results. Completed those miscibility and immiscibility tests with the methanol, ethyl acetate, acetone. You already saw the MTBE and methylene chloride, and you can see this one. See, it's not as easy.
It is not as easy as it looks. You can see the data right here, so make sure you record that. One thing that I'll point out is methylene chloride is an organic solvent that has halogens in it, so it's CH2Cl2. And halogens, they have more protons and neutrons than oxygen or carbon, and that makes them more dense. So as far as top or bottom layers, you'll note that the organic solvent is usually the top layer, but when we have one with halogens in it, it does sink to the bottom layer because of that extra density, or the more dense halogen atoms. So that's kind of a unique thing about halogenated solvents. I think that's good. All right, we're going to move on. All right, so we went through those extraction concepts, allowed you to fill in those first 2 tables. And what's kind of the take-home messages here? Well, what we want to look at is were the solutes charged or neutral? And we looked at 3 different solutes. They included sodium chloride, which we know is an ionic complex, sodium plus, chlorine minus. And what was the solubility there? Well, sodium chloride is really soluble in water. It's really soluble in aqueous things. It was not soluble in the organic solvents. What's the next solute we looked at? Benzoic acid. So what is benzoic acid? Benzoic acid has a bunch of carbons like this, and then it has a carboxylic acid. So that carboxylic acid functional group was neutral. This molecule as a whole is neutral. There are no charges on it. It has some dipoles, but no full formal charges. And what we saw is that this carboxylic acid was soluble in the methyl tert-butyl ether, but it was insoluble in water. So we saw that this was soluble in organic solvents, but insoluble in aqueous solvents. What is the third molecule we looked at? It was sodium benzoate. So it's the exact same molecule as this, but it's been deprotonated. So it is actually a charged molecule. Sodium benzoate looks like this. So again, an ionic molecule. What did we see with sodium benzoate? Even though it has all of this organic on it, it's still insoluble in organic solutions. It's insoluble in that methyl tert-butyl ether. So what really matters then? Charge is what really matters. So if we have charged molecules, they are aqueous soluble. And we have neutral molecules, they are organic soluble. So that's pretty much it. What else did we see? Miscibility versus immiscibility. If molecules are smaller, they're going to be more soluble with water. So if they have fewer carbons. So yeah, we'll put something up here for that. Miscibility with water. So let's look at the molecules. We have methanol, methanol. We had ethyl acetate. We had acetone. We had a methyl terbutyl ether. That's methyl terbutyl ether. And we had methylene chloride. So it's carbon attached to two H's, two Cl's. And we saw that we had miscible molecules over here and immiscible. Immiscible, is that? Yeah, that's a word. Immiscible over here. So essentially, what impacted their miscibility? Well, when there were fewer carbon atoms, there's 3 here, there's 1 here, 2. So a larger number of oxygens for every carbon made it more miscible. We have that breakdown a little bit with ethyl acetate here. Ethyl acetate technically has 2 carbons. I'm sorry, 4 carbons, 2 oxygens. But miscibility is sometimes hard to predict. Sometimes we just have to go with experimental observations. Essentially what this means is that if we're doing an extraction, we have to use solvents that do not mix with water in any proportion. So these would be not suitable of a solvent for extraction, while these 3 organic solvents don't mix with water, so they could be used in an extraction experiment. So that kind of finishes up everything we're talking about before we get into the major experiment, where we are taking a mixture of 3 molecules, and we're going to be using our understanding of miscibility, immiscibility, of solubility and insolubility with molecules, and also connecting that to acid-base chemistry. We saw that acid-base chemistry can be used to protonate or deprotonate different molecules, and if they're protonated versus deprotonated, that is going to impact if they're charged or not, and if they're charged or not, that is going to impact their solubility. So we will see that we'll be able to separate a 3-component mixture using extraction techniques. So look forward to that and enjoy the experiment. It's kind of one of my favorites throughout the semester, so hopefully it works well by this virtual lab method. All right, so now we are on to the second part of this experiment, where we are obtaining a 20 milliliter sample solution of 3 compounds. And those 3 compounds are benzophenone, meta-nitroaniline, and meta-nitrobenzoic acid. The M stands for meta-N. And that's what we have right here. This 20 milliliters of a solution of all 3 of those things. And the goal of an acid-base extraction, or of an extraction in general, is to separate out components of a mixture, or essentially purifying molecules, so removing different components based on their solubilities.
And I don't know if you noticed, but the solution has a light yellow tinge to it. I don't know if that came through on the video, but you can see it's a light yellow tinge to that. And what we've also done is we set up a thin layer chromatography plate for the experiment, so I can show it to you here. What you have is 4 lanes across the bottom. S is for the sample, and that's the material that's in the graduated cylinder there. And then there's a lane B for base, A for acid, and for ore. So right now, all I have spotted on there is the sample. And I've got the UV lamp here, so I can show you that. If you remember with TLC, you always want to verify that you can see what you need to see. So there you can see just above the S, that darkish spot. So that is our starting sample. And as we complete the extraction, we'll be spotting the different organic phases that we get from that on the different lanes, and then we'll come back and develop that and see how we did with our separation.
And here is, just to compare that to what our report sheet looks like, we have right here is that TLC plate that we're essentially doing. Yeah, so we will be back with more parts of this experiment.
I'm comparing to the report sheet that our plate did not match the one in the manual, so now if you look at the bottom of our plate, we've adjusted the aqueous acid and aqueous base to match what's on the report sheet now.
They were flipped a moment ago, but now they're right, so it'll look perfect.
We are ready to roll.
All right. Here we have our separatory funnel. This is what we are going to be putting the different solutions into and shaking. So I'm going to put that here on our ring stand, and I'm going to add our 20 milliliters of that 3-compound mixture in here.
Remember, that's mostly methyl terpyl ether with small amounts of the 3 components.
Exactly.
So basically an organic solution.
And now we're going to add our 10 milliliters of 1 molar sodium hydroxide to that. That measured out already. And then what you do in an extraction is you have to shake the separatory funnel to really mix those layers, because at this point you can see that there are 2 very clear layers and they're not really mixing, they're only mixing at that interface. So what we do is we shake it, and that allows those layers to mix more thoroughly. So essentially you put the stopcock on there, you hold that down, and then you can invert it. You can vent it like that. It just did a little, and then you essentially shake it a lot, let it settle down, and just do that a few times. And you can see when I immediately shake it, it kind of looks like one layer. But then when we wait for a minute, it's going to settle out into 2 layers. And we have, again, our organic layer on the top because it's mostly MTBE, and then our aqueous layer on the bottom. So now we're going to separate these layers, and we're going to add them to different Erlenmeyer flasks. Okay, now we are going to drain the bottom water layer, which is our 1 molar sodium hydroxide layer, into this Erlenmeyer flask that has aqueous base on it. And you can see the 2 layers has the interface right there. So I'm going to slowly drain that into here just until we get to that organic layer. Slowly letting that in there. And that should be good.
This part is very similar to the burettes you would have used in Gen Chem 2 doing titrations. Just draining liquids through a stopcock, but in this case trying to stop it at the interface between the organic layer and the aqueous layer.
The procedure says we're going to do that another times with 10 extra milliliters of sodium hydroxide, of 1 molar sodium hydroxide, and then we're going to also add 5 milliliters of water to the separatory funnel, shake, vent, and also drain that into our aqueous base Erlenmeyer flask. So
ultimately we'll wind up with 25 milliliters of aqueous solution, 10 from the first sodium hydroxide, which you already saw,
yeah.
10 more sodium hydroxide that will add to it, and then 5 milliliters of water that will also add to it. So extracting it 3 times with those different solutions.
Here's our 25 milliliters of the aqueous base solution. We still have the 20 mils of the organic layer in the separatory funnel, and we're now moving on to the next phase of the acid-base extraction, where we are adding the 1 molar HCl.
Yep, so it's a very similar process. We'll start with 10 milliliters of 1 molar HCl, shake, vent, drain that out. Then we add 10 more milliliters of 1 molar HCl, shake, vent, drain that out. And then we add 5 milliliters of water, shake, vent, and drain that out. So we'll wind up with 25 milliliters of aqueous acid in a separate Erlenmeyer flask. And we'll report back when we get that part done.
So now we've completed the acid wash steps. So we have our aqueous acid. So it says right there. Oh, it's kind of hard to see.
And then this is the leftover organic layer that we drained out of the separatory funnel. In general, with working sub funnel, the bottom layers go out the bottom through the stopcock. The top layer would go out through the top, pouring it off. So we poured the organic layer that was left in the sub funnel into this one. So now we have our 3 flasks. We've got the aqueous base, which was the first extraction that we did. We've got the aqueous acid, which is the second extraction that we did, and then we've got the leftover organic layer here.
And one thing that happened in this last extraction was that with the aqueous acid, after we added that, the organic layer, it was a yellow color, and now it's clear, so something must have happened to cause that color change.
Some chemistry going on there, so we had a color change from yellowish to clear in the organic layer when we extracted with that aqueous acid.
So it's always good to think about, when we have our molecules in the background, what the heck is happening to these things when we're treating it with sodium hydroxide? What's happening to it when we treat it with an HCl solution? So that's what we should be thinking about. How are these molecules being modified, and how would that impact their solubility? Also needed to check the pH of our different solutions. So we have our aqueous base solution. This was the first one that we did. I'm not even going to aspirate any. I just dipped the tip of this pipette in there. And here we have our pH paper. And actually, if you could hold that, we can see the color change. So we can compare it. It looks pretty similar to that 11.
Yep, so somewhere around 11. Very basic.
Also want to know what our pH of our acid solution is. Here's that. Again, I'm just grabbing a pipette tip. And you can see here was where we did our base one. Now we're doing the acid. There it is. It's about 1.
About 1.
Aqueous base flask here. It says, now take the aqueous base flask and carefully add 5 milliliters of 6 molar HCl.
Do you want a pipette?
Sure. I can actually just use this one. Actually, here we go. This one's good. So we have our 5 mils of the 6 molar HCl here. 6 molar HCl here. We're going to drip this into the aqueous base. And that's that. So we'll swirl it around a little bit. And let's check our pH. So I'm going to just use the same thing. I'm going to pipette it up and down to fully mix that. I'm going to pull the bulb off, and we can see, it's kind of hard to see there, but we can see our aqueous base was the blue color, and now when I hold it up here, you can see it is fully red. I think you can see it. There we go. So we have acidified that layer. This acid solution, we already checked its pH, and it was near 1, very acidic. So now we're going to add our base solution to that and see what happens. So we're adding our 6 molar sodium hydroxide.
Well, if you can see, there's a little, hold on a second.
Looks like it's turning
Little
yellow.
color change, yeah. So let's put a white bottom underneath that. And so when you see the base go in there, you can see a yellowish color.
Yeah, it's really nice.
Almost like that phenolphthalein indicator during a titration. Okay, and there the yellow color is persisting.
I think that might have been me. All right, so we have added our sodium hydroxide to that. Let's check that pH. That solution. Fully mixed. All right, let's take a little drip of that. See, we are very much in that 11 color.
Yep. All right.
So we've added enough. So now we've recorded the final pH once we've added the 6 molar HCl or the 6 molar sodium hydroxide to the different aqueous base or aqueous acid flasks.
Yep.
Now we are adding about 5 milliliters of methyl tert-butyl ether to each of these. Yep. And that is what we are ultimately going to be taking a sample from to spot on the TLC plate.
That's right. So we've got the aqueous base here that was acidified at 5 milliliters MTBE. Shake it around to let the layers mix, and then we'll be spotting the organic layer onto the TLC plate. And then we'll do likewise with the aqueous acid one that was basified.
So it's kind of important to note, it says aqueous acid, but right now, this is basic. We just saw that. So same with that one.
We'll report back.
All right, so we've added our MTBE to these, and what you can see with the Erlenmeyer flask is that we clearly have 2 layers now, the top layer, the organic layer, and the bottom layer being the aqueous layer. And you can see the color of the one that turned yellow is now in the organic layer.
Yep, the other one didn't do anything all too interesting, just the 2 layers. So what we'll do now is we're going to spot the organic layer from each of these flasks onto the appropriate lanes of our TLC plate, and then we'll get that TLC plate developing, and we'll report back when it's done.
All right. All right, so we're just making sure we have our spots on the bottom of the plate. We're about to put it in this TLC chamber, and you can see the kind of darker spot indicating that we did spot each of those. So we are ready to go. All right, so we ran our TLC plate of this mixture of compounds that we're trying to separate. This is what our data looked like on the TLC plate, and we have brought that over to the report sheet. So you guys should be filling in what that looks like. And you can see that we did separate out the 3 components of the mixture. Anything else to say?
Not right now.
All right. All right, so that should have been all the information that you need to fill out the remainder of your report sheet and then also finish all of the questions. So let us know if there's anything else you need, but we're pretty sure you're good to go.
Yep. Have fun.
Yeah, have fun.